James E. Kelly, who's part of the Remington Rand, and Morgan R. Walker, who's part of the DuPont. They both developed the critical path method. James E. Kelly and Morgan R. Walker played a significant role in creating this project modeling technique. They shared ideas on how the critical path method can be utilized to optimize project scheduling. It helps identify the longest sequence of dependent tasks and determines the shortest possible project duration. On this video, we will be discussing on finding the critical path on a project network. Analyze, plan, and schedule is what we are going to do to achieve our project. On a project network, tasks are represented as nodes, and arrows indicate dependencies. Predecessors are tasks that must be completed before the next task can begin. And each task has a corresponding duration. Here, to understand the table, A stands for tasks. T stands for days. ES stands for earliest start. EF stands for earliest finish. LS stands for latest start. And LF stands for latest finish. Now, I will show you how to do the CPM network diagram. I will be working on this data to create the CPM network diagram. These 9 activities have corresponding predecessors and times. We have activity A, B, C, D, up to I. Activity A has no predecessors while activities G, H, and I each have 2 predecessors. Now, let's dive into arranging our activities. We'll start with activity A, which has no predecessors, and then sequence the remaining activities based on their dependencies. Activity A serves as the starting point since it has no predecessor. Activity B needs A to be completed before it can start. Also, activity C needs A to be completed before it can start. Activity B and activity C both depend on the completion of activity A. Therefore, they follow activity A in our sequence. Continuing on, we identify the tasks that depend on the completion of previous activities and arrange them accordingly. For example, activity G depends on activity D and E. And activity H depends on activity E and F. We repeat this process until all activities are arranged based on their dependencies. Since activity I is the last, it goes to finish. With our activities arranged, it's time to perform the forward pass. But before that, first we will need to identify the time of each activity and ensure they correspond to them. But before, we will need to identify the time of each activity to ensure they correspond to them. And we will continue filling in the blanks for ES, EF, LS, and LF. A has a corresponding time of 5, B has 10, C has 13, D has 7. E has a corresponding time of 3. F has 9. G has 4. H have a corresponding time of 3, and I has a corresponding time of 7. Moving on to the network, during this step, we'll calculate the earliest start and finish times for each activity, ultimately determining the earliest possible project completion. The first thing we need to get is the earliest finish. To get the earliest finish, we need to add the earliest start and time. We will begin by setting the earliest start time for activity A as 0 because it has no predecessors. For each subsequent activity, we'll calculate the earliest start time by considering the earliest finish time of each predecessors. Since A has an earliest finish time of 5, B will have an earliest start time of 5 and get an earliest finish time of 15. Also, C will have an earliest start time of 5 since A has an earliest finish time of 5, and C will get an earliest finish time of 18. We'll continue this process for all activities, ensuring we accurately determine the earliest start and finish times. B has an earliest finish time of 15, so D will have an earliest start time of 15 and get an earliest finish time of 22. Also, E will have an earliest start time of 15 since B has an earliest finish time of 15, and E will get an earliest finish time of 18. C has an earliest finish time of 18. F will have an earliest start time of 18 and get an earliest finish time of 27. Activity G depends on activity D and activity E. Since D has an earliest finish time of 22 and E has an earliest finish time of 18, to get the earliest start time of G, the highest earliest finish will be chosen. In this case, it's 22. So G will have an earliest start time of 22 and get an earliest finish time of 26. We will continue or repeat this process on activities H and I. Since 37 is the earliest finish time of I, the expected output project is 37 days. Now, we will do the backward pass. To get the latest start time, the latest finish time should be subtracted to activity time. Since 37 is the earliest finish time, the latest finish time of activity I will be 37, and the latest start time is 30. I have a latest start time of 30. G will have a latest finish time of 30 and get a latest start time of 26. Also, activity H will have a latest finish time of 30, since activity I have a latest start time of 30, and H get a latest start time of 27. Activity H has a latest start time of 27. Activity F will have a latest finish time of 27 and get a latest start time of 18. G has a latest start time of 26. D will have a latest finish time of 26 and get a latest start time of 19. G has a latest start time of 26 and H has a latest start time of 27. In this case, the lowest will be chosen. So E will have a latest finish time of 26 and get a latest start time of 23. We'll continue this process for all activities. After that, we will find the slack of each activity. To find the slack, we need to subtract the earliest start time to latest start time and subtract the earliest finish time to latest finish time. Activity A has a slack of 0. Activity B has a slack of 4. C has a slack of 0. D has a slack of 4. E has a slack of 8. F has a slack of 0. G has a slack of 4. Activity H has a slack of 0. And activity I have a slack of 0. So, to determine which activity is on the critical path, you will look at the slack that is equal to 0. Now, we can identify the activity that is on the critical path. We can see that activities A, C, F, H, and I are part of the critical path.